Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 14th, 2026, just 1 week ago. It introduces a cross-embodiment alignment method that transfers human tactile signals to robots, improving success rates on contact-rich tasks by roughly 60%. The paper is titled TactAlign, Human-to-Robot Policy Transfer via Tactile Alignment. And as we'll see later, the results for zero-shot transfer on unseen objects are really impressive. Figure 1 illustrates the complete TactAlign pipeline. On the far left, input data comes from humans wearing tactile gloves and robots collecting separate data. The middle section details the core innovation, using self-supervised learning and cross-sensor alignment via rectified flow. Rectified flow is a technique that learns a direct transport map between two distributions, effectively translating human touch signals into the robot's feature space. Finally, on the right, the robot uses this aligned policy for complex tasks like pivoting a box or screwing in a light bulb. Figure 2 details the specific architecture behind this process, which operates in two distinct stages. In step 1, shown in the large blue and red blocks, the model independently pre-trains encoders for the robot and human using self-supervised learning. The blue pipeline processes Zila sensor images, while the red pipeline handles time series data from the Osmo glove, both compressing inputs into latent vectors. Then, the rightmost panel illustrates step 2, the alignment phase. This component uses a velocity field to transport the human latent H into the robot's latent space, effectively translating the human's tactile experience into something the robot understands. While Figure 2 detailed the alignment training, Figure 4 shows the deployed action policy architecture. The system takes tactile input from either the robot, shown in blue on the left, or the human, in red. Notice the purple ODE solver block in the center. This component transforms human signals into the robot's latent space, using the learned velocity field. On the right, a shared proprio encoder handles kinematics like fingertip locations. Finally, these features enter the yellow transformer decoder at the top, which predicts the necessary action sequence. So Figure 5 visualizes the result using UMAP projections. The leftmost summary panel compares the distributions. Green is the original human data, and blue is the target robot data. The red points represent human data after transformation. Notice how the red cluster moves to overlap almost perfectly with the blue robot distribution. The remaining panels color these points by force magnitude. They confirm that the alignment preserves physical meaning because high-force human touches, shown in red and yellow, map correctly to corresponding regions in the robot space. Well, having seen the alignment in theory, Table 1 now quantifies the success rates. It compares TactAlign against baselines across 3 tasks: pivoting, insertion, and lid closing. The first row, robot only, reveals a critical limitation. While it scores 100% on known objects, it fails completely, dropping to 0 on objects only the human used. In contrast, the bottom row shows TactAlign bridging this gap. For instance, in pivoting, it hits 83% on human-only objects. Even for lid closing, a task the alignment model never saw, the method generalizes robustly, lifting the average success rate to 79%. Moving to Figure 9, we see the most impressive demonstration, the light bulb screwing task. The red box on the top left shows the human operator providing the tactile signals. Crucially, the blue panels show the robot performing this task zero-shot, meaning it never saw any robot data for this interaction. It successfully transfers the human's dexterity to the robotic hand, culminating in the bottom right frame where the light bulb turns on. Wrapping up, TactAlign proves that robots can inherit human dexterity without requiring identical sensors or strictly paired data. By aligning tactile representations in a shared latent space, the method unlocks robust zero-shot performance on complex tasks. This suggests that tactile alignment is a critical step toward general-purpose robotic manipulation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.